Hello. Now we are going to look at some geometry involving circles. And the very first thing to say is anytime we're dealing with circles, the center of the circle and any radii or radiuses that we can see are the most important things to look for. There's lots of other facts we need to know, but as a general rule, can we see the center of the circle? And that can help us with lots of problems. And can we see any radius lines? And they're often connected to finding the solution to lots of problems. So they're the two pieces of information we always want to look for. We won't always have them, but they're what we should start looking for. Now, we have a theorem here that is quite important. The angle at the center of our circle is going to be twice the angle at the edge of the circle. So what we have is lines going in towards the center and going out towards the circle, and they're starting from the same points on the circle. So we're starting from that point and that point, and if we go to the center and out again, or to the circle and out again, we have this pattern of the angle, how have I said it? The angle at the circle, x, is half of the angle at the center, or the angle at the center would be double the angle at the circle. So we need to have that in the back of our minds. It's a tool that comes up in a few different circle geometry type questions. Now, building off of this rule, what would happen if our points where we're touching the circle here ended up in line with, or forming a straight line with, the center of the circle? Well, then we'd have a diameter line of our circle. That's what we have in our second circle down here. So this is actually exactly the same type of diagram as we have here. It's just a special case of it, where we have the diameter line, so one of the lines here going straight through the center of our circle. We still apply the same rule. What angle would be in here? Well, it would be 180 degrees, because that's the number of degrees in a straight line. Well, we should have half that angle at the circle. So we'd have 90 degrees. Half of 180 is 90. So this gives us a rule that can be useful for lots of different problems we can be given. If we have a triangle sitting in a semicircle, so the diameter line is the hypotenuse of our right angle triangle that we end up with, then we are able to immediately say, if we have the diameter line as the long side of our triangle, then this angle up here must be 90 degrees. And that can help us in lots of different situations. And it's just a special case of this more general rule. Now, where we have lines crossing circles, we have some other things that we need to keep in mind. And they're similar ideas. This is the more general case. This is a special case, just like we had up here. In general, if you have a line crossing a circle, where it crosses the circle, so this bit in here, where the line is crossing the circle, is called a chord. And if you get the perpendicular bisector of that chord, that line, the perpendicular bisector of the chord, goes through the center. Now there's a lot of technical language there, but perpendicular just means at right angles. So if we have a chord and we go, bisector means to cut in two. So if we cut the length of the chord in two, so effectively we're at the middle of the chord, and we go out at 90 degrees from that point, then we go through the center of the circle. So if we cut the chord in two and go out perpendicularly or at 90 degrees from that midpoint, then we're going to go through the center of the circle. And this can help us to find lots of things about circles. Now, what happens if our chord only just touches the circle? So we don't have 2 points of contact, but only one. Well, the same fact is going to be true, but then we call that chord, where it just touches the circle instead of cutting it at 2 points, we call that line a tangent line. It's just touching the circle at 1 point. But this rule that we looked at still applies. We go at 90 degrees, so perpendicularly out from the point of contact, and that line that I've drawn in here in blue goes through the center. It's the same rule as this, but it looks a little bit different because there's only 1 point of contact for a tangent. That's the same idea. So those are our different facts that we can use to solve circle problems. So let's use them now to solve some of these problems. If I want to know this angle x, and I can see that I've been given the center would be marked with a bit of a dot. My first job is going to be to identify the center and any radius lines. Well, I have the center given to me, and I know that this length and this length are the same because they are radius lines. May not need that for this question, but I'm always having that in the back of my mind for any circle geometry type questions. Can I see the center? Can I see any radii? And I know that the radius must be the same length for all of them. So what do I have here? Well, I'm coming from points on the circle, and I go to the center, and I also go out to the circle. So that makes me think of the first thing we talked about here. This angle here is going to be twice as big as the angle out here. So 2 times x is going to be this angle, and it's 140. So I know that this angle here must be half of 140, which is going to be 70. And that's all I have to write down. I'm expected to know this fact, that the angle at the center is twice the angle at the circle. So all I have to write down is what I have here. I have this angle is twice as big as that angle, and then I just find that my angle I'm looking for must be 70 degrees. Now, I have lots of lines drawn in here, so I have my circle, I have my center marked, so I'm looking at my center. I have some radius lines marked. I have this line is the same length as this line, and I'm also told that that line is the same as the 2 radius lines. So this length here must be the same as the radius. And I can also see another radius line here, so I'm going to mark that in. That length must be the same as the ones marked here as well, because they're all radii. Now this doesn't have to be the same length. I'm not told that it is, so I can't assume it. I was told that this was the same as the radius, so that's okay. What else can I see about my diagram? Well, I can see that I'm going from circle edge to circle edge, and I'm going through the center. So this line here is a straight line that's the diameter of the circle. So that means that this angle here is straight line angle is 180. So this angle up here must be 90 degrees. So this total angle in here must be 90 degrees. And that can help me to solve my problem. So what else do I know? Well, I know that I have an equilateral triangle in here because all the side lengths are the same for this triangle, the little triangle in here. So that means that all these angles are the same, so they're all 60. They're 180 broken up into 3 equal pieces. So they're all 60 degrees. So I could use that to find x and to find y. So I can say that this total angle up here must be 90 degrees. And I know that this bit is 60, so how would I find x? Well, x plus 60 degrees must add up to 90 degrees. So I can rearrange that equation, and I know that x is going to end up being 30 degrees. That's my first letter found. I can do a very similar argument for y, because I know that this is a straight line, so y plus 60 must add up to 180, must add up to 180. 180 degrees in a straight line. Again, rearrange and I get 120. So I know y is 120. Now I could just add up the angles. X plus y plus z must add up to 180 in order to find z. However, I also know that z has to end up being the same as x, because I see that this triangle is isosceles. So we're using a lot of our facts about triangles to solve this circle problem. So because this length is the same as this length, they're both radii, the angles opposite equal sides in an isosceles triangle must be equal. So I would be able to say that x must be equal to z, which I already know x is equal to 30 degrees. Or I could say that x plus y plus z adds up to 180. I know what x and y are, so I could solve for z. That would be fine too, but if we can see things like our isosceles triangles, that's an important skill to have. Now, what do we do for our situation here? Well, I have another diameter line, so that means that this angle up in here is going to be 90 degrees. And I know the radius is 13, so I'm going to write that in. So that length there is 13, that length there is 13. That means in total, that length has to be 13 plus 13 is 26. So I have a right angle triangle, and I'm looking for, I know two of the sides and I'm missing my third side. Well, I know how to solve that type of problem. I'm just using Pythagoras for that. So we can see how much of our triangles work comes into our circle type questions. So 26 squared, that's my diameter line, my hypotenuse across from my right angle, is equal to x squared plus 24 squared. And when I put that into my calculator, I get 676 is equal to x squared plus 576. Now I'm just solving my equation. 576. So I get that x squared is 100. Square root of 100 is 10. And I'm not interested in the negative case because this is a physical length of a side, so x would be 10 units. Now, if I know that the length of AB, this is a chord of my circle, the length of AB is 8, how would I find the radius? Well, I can see that I'm going perpendicularly out from my chord to the center. So that means that that must be the halfway point of A and B. So that means that that length must be 4 and that length must be 4, because the perpendicular bisector of the chord would go through the center. So working backwards, I know that those lengths have to be 4. I draw in the radius because I was asked about it. So a radius line would be that one, or I could draw that one as well. They must be the same. So how would I find the radius there? Well, I just use Pythagoras again. So I'll write that out. And when I write all of that out, I write out my Pythagoras, I sub in everything. My radius is the side that's across from my right angle, so it's the hypotenuse. I sub everything in and I get my radius must be 5. Now here I have a tangent to the circle. I have a line from the tangent to the center. So that tells me immediately that that must be a right angle in there, because the perpendicular to the point of contact goes through the center. So that must be a right angle. I have the radius is 8. So this length here, I'd also say must be 8. And I have a side length here of 15 for what I can now see as a right angle triangle. And I want to find the length x. Well, I can see a right angle triangle here. So I'm going to say that I have this length here is something I can find. So I'll call that y. And I'm going to try and find that hypotenuse length. It's across from the right angle, so that hypotenuse length. And then I could use that to find x. So I'm going to write out my Pythagoras now. So when I write out my Pythagoras to find my green length of y, I find that at y, the total length of the hypotenuse ends up being 17. And I can see, the reason I found that is because I could see that I could, but I can see that it's connected to x, because x plus 8 must add up to our length of our hypotenuse. That's what I have written up here. So I now know that 17 is equal to 8 plus x. This plus this must add up to my green length of y that I found was 17. So then I just rearrange that to get x by itself, and x must be equal to 9 units, or 9 would be equal to x, the way I had it written around. So that is how we can use our facts about circles combined with what we know about triangles, particularly Pythagoras, as we can see, to solve our geometry questions involving circles. And that is what we need for now.